Hello, everyone, and so we're welcome back to episode 8 of my series. This is probably, of episode 8, what I'm going to go over in this video and probably the next one, maybe even a third, depending on how long it is the part of my research that I'm currently the most excited about. And hopefully after it's over, after we cover it, you will see why and agree with me. So, last time, what we did is we worked with my PQ-adic Wiener-Tauberian theorem, and we combined it with the correspondence principle to do spectral theory. And so, in particular, what we saw was that the reciprocal of a function will be that if our function is in a unital Banach algebra, the reciprocal will also be in the unital Banach algebra if and only if the span of the translates of F's Fourier transform are dense in a certain other Banach algebra. In particular, this other algebra is the image of the Banach algebra we started with under the Fourier transform. In this case, the spectrum of F was then the set of scalars lambda for which 1 over lambda minus f of x fails to be an element of our initial Banach algebra. And thus the analogy is that the eigenvalues of a matrix are precisely those such that lambda times the identity minus matrix has a zero determinant, in which case lambda identity minus matrix is not invertible. So what we can do with this is to just note formally, if we just pull out a factor of lambda, we have this geometric series expression. One way to make this completely rigorous would be to show that that f over lambda has a norm strictly less than 1 in where the norm is from the Banach algebra containing f. In this case, the series here would then honestly, genuinely converge with respect to an element of the Banach algebra, and this would then prove that lambda minus f of x had an inverse, which was in the Banach algebra, and so this criterion then is sufficient to prove that lambda is not an element of F's spectrum. This has to do with what's known as the spectral radius formula, which is very important in functional analysis and operator theory. So, of particular interest, as we said, is when our unital Banach algebra admits a form of the Fourier transform. Using the fact that the Fourier transform is a linear operator, and in fact an algebra isomorphism, which turns multiplication into convolution, note that again, formally, the Fourier transform of this, if it exists, is 1 over lambda times the sum, lambda to the n. And here we have the nth-fold convolution of f hat with itself, where by definition, f hat star 0 is defined to be f of 1, the image of the unit of the Banach algebra we started with. So, because the Fourier transform is an isomorphism onto its image, another way to show that lambda is not an F spectrum would be to prove, for example, that f hat star n exists for all n, and that this formula then is then the Fourier transform of an element of our original Banach algebra. If we then apply Fourier inversion, we will recover an element of our Banach algebra, which is of course equal to 1 over lambda minus f of x. Yeah. More generally, it seems quite also remembering the Wiener-Tauberian theorem. If 1 over lambda minus f is an element of the Banach algebra, and this series converges, then this thing, by Wiener's Tauberian theorem, will have translates whose span is dense in a certain other Banach algebra. For lack of better purposes, I'll call it the Fourier transform algebra. And so, even without knowing whether or not this converges, by studying, in particular as we consider the partial sums, by studying this quantity and its behavior of its translates, we can do what we were doing in the previous video with all of our matrices and inversion. We can do it, but from the back door, if you will, rather than having to work with the inversion being, without doing it explicitly, by computing these convolutions, we would be able to know those reciprocals and residuals and everything. We'd be able to know it explicitly. So what this says then is maybe we should try in investigating not just chi. So we've been investigating chi q. What if we investigate chi q to the k, a product of chi q with itself, k times, and then investigate to see if that object has a Fourier transform. If it did, we could then start studying this series and potentially get something useful. So now here's where things get a bit technical. If a function f from z2 to zq is continuous, then f squared is going to be continuous. And by the fundamental theorem of p-quadratic analysis, which says that every continuous function has a uniformly convergent Fourier series representation, and vice versa, then so if you have a continuous f, then f squared is also going to have a Fourier series representation. And the reason because of this is that we know that if f is continuous, f hat will then have to decay to 0 quadratically at infinity. And we know that the convolution of any two such f hats is always going to be convergent because of the ultrametric structure of the quadratics. So what the problem here is that chi q hat does not decay to 0 quadratically as t approaches infinity, and that's because chi q is not a true function, but rather is a measure. And so just to recall, measures in this context are those p-quadratic functions whose Fourier transforms do exist but do not decay to 0, but are nonetheless bounded, whereas continuous functions are those Fourier transforms, functions whose Fourier transforms exist and decay to 0 quadratically. So the fact that chi q hat does not decay to 0 quadratically, it would immediately tell us that the convolution of chi q hat with itself, chi q 2 star, would be undefined. This is just like the product of, the convolution of an L1 function with an L1 function is again an L1 function by Young's convolution inequality, but the convolution of an L infinity function with an L infinity function, that might not even exist because the two functions might, their convolution product thingy might not be integral. In fact, it almost never will be. And this actually reflects a fundamental property of measures and distributions that analysts get drilled into us, which is that the pointwise products of two measures is not, in general, a measure. When you're dealing with measures, there are really two natural ways to multiply them. The first is, and this is by the product measure construction, and this is the same as the tensor product of two measures, and we can approach that from linear algebra just by saying that we can get if we have two linear maps, we can tensor product them to get a bilinear map. And the standard example of a product measure would be how the area measure in the plane is usually written as dx dy. Technically speaking, that's the tensor product of the horizontal measure, dx, and the vertical measure, dy. Another way to multiply measures is by taking their convolution. In this case, what this does is by the Fourier-Stieltjes transform, the Fourier transform of the convolution of two measures gives us the product, and if both our measures are going to have L infinity Fourier transforms, and we know that the pointwise product of two L infinity Fourier transforms is again going to be an L infinity Fourier transform. However, the pointwise product, that is d mu of x times d nu of x, that isn't really going to work out very well, and in general you can't make it work. A classic example of this is the Dirac delta distribution, which when we integrate f against the Dirac delta, it results in evaluation. But what does it mean to integrate f against the square of the Dirac delta? That's undefined. Even though we can make sense of the derivative of the Dirac delta, we can't make sense of the square. So, of course, if you've gotten this far in the series, you're probably expecting me to come out and say, but wait, actually, yes, we can compute the Fourier transform of chi q squared, and, of course, you would be right. As it turns out, we can show that chi q to the k has a Fourier transform for every integer k greater than or equal to 1. We can even compute these Fourier transforms explicitly, though it gets exponentially more painful as k increases. So, because this computation is so awful, I've basically spent the better part of a year trying to make it work. Rather than work with chi-q directly, we will instead work with a related but simpler function, namely the F series xqp. So in a previous episode, I'm pretty sure I wrote this as pq, but I'm now writing it as qp, and I will go back later when I publish this as a textbook and fix its convention. This is, just trust me, I'm going to write it like this. It keeps us from losing our minds. So here, let p and q be co-prime integers, none of which are -1, 0, or 1. And then we're going to consider this F series, and this is going to converge in the simple, this should be a P. It's going to converge in the simple PQ, 2Q, this is correct. It's going to be converging in the simple 2Q Adic frame to a rising continuous function. That means when Z has infinitely many ones digits, we use the Q Adic topology. And when Z has finitely many ones digits, we use the real topology. And then, so this is going to be rising continuous, and then it is the unique 2Q adically rising continuous function satisfying this system of functional equations over the two adics. And so the proof is just standard. The F2 convergence for the F series follows by the arguments we gave for chi-q back in episode 1, and then directly, and just like we did in that episode, directly substituting 2z and 2z plus 1 into this F series will get us the functional equations. Yeah. So now what we're going to do is we're going to consider x to the r. So let r be a positive integer. And then for each k greater than or equal to 0 integer, I'm going to write fk of z to denote the kth power of xq2. So that means f1 is equal to this with a 2 in the denominator. f2 is its square, f3 is its cubed, etc. And by convention, f0 is going to be 1. Then we have the following functional equations. Fr of 2z is equal to sum from k equals 0 to r of r choose k, fk of z over 2k, and fr of 2z plus 1 equals sum from k equals 0 to r of r choose k, qk over 2 to the k, fk of z. Moreover, for any not positive integer r, fr is the unique 2q adically rising continuous function which satisfies these functional equations in the sense that if I give you a rising continuous function g, which satisfies these equations, then g must be equal to fr. The thing here to note is that fr of 2z depends on fk for all of the k's, including k equals r. Yeah. So now if we let frn denote the nth truncation of r, this means that we precompose f with the map z mod 2 to the n. We then have that these functional equations yield this recursion relation. And the only part of this argument that requires any elaboration is the uniqueness of fr as the solution of these functional equations. To that end, suppose we have a rising continuous g satisfying this equation. Setting z equals 0, we get this. And from the top equation, we can solve for g0. No, we don't even need to know what the values of fk of 0 are. It's just we can compute them in closed form. And in particular, note that we omit the k equals r term. So what this says then is that the value of fr at 0 is determined entirely by the values of the fk's at 0 for all k strictly less than r. More generally, by using these functional equations, we can then get formulas for g of n for all non-negative integers n, and in particular for having solved for the values of gn for n between 0 and 2 to the big N minus 1, the functional equations will then tell us that the values g of 2 to the big N through blah 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 g of 2 to the big N plus 1 minus 1 are then completely determined recursively by the values of that g takes for n in this range. In this way, the shape of the functional equation uniquely determines its solution, and then we have that the restrictions of g and fr to the non-negative integers are equal, and then by rising continuity, when we extend to a function on z2, we then get that g and fr equal everywhere on z2, and we're done. So now we're going to proceed as we did with chi-q. We're going to take the Fourier transform of frn. The reason why we can do that is because frn, which is fr of z mod 2 to the big N, that's a locally constant function, and so we can compute its Fourier transform. Naturally, this is when you directly rewrite the Fourier integral of f hat of Rn, you would get this. This is just literally from retaking the integral, the Fourier integral, and using the fact that fr comma n is locally constant mod 2 to the big N. With f hat of r0 of t is 2 to the r times the indicator function of t, the indicator function of 0. And in particular, we then have that f hat Rn satisfies the following recursion relation for all t and n. So, do I give a proof of this? No. So the proof of all this is it's straightforward. All you do is you quite literally just use these equations. It's as we did with chi3. We use this. We then break this sum up into the sum over fr of 2n and fr of 2n plus 1, and then we apply these functional equations here, and that will give us our result. So at this point, in the corresponding analysis we did of chi-q in episode 4, what did we do? Well, having obtained this recursive relation, we then nested this and solved it explicitly for f hat Rn. And then what we did is that we saw that in our analysis, the key step was to study how qn hat of t behaved as n tended to infinity for fixed values of t. The punchline in all of this is that in the closed form expression for qn hat, we found that there were products of the following form, where g hat of 2 to the nt, where g hat was some function of accepting variables from z to hat. The trick, then, that we used for our untangling was the observation that once the upper limit of the product was bigger than the power of 2 in the denominator of t, the fact that g hat is periodic modulo 1 would then tell us that once n is bigger than negative v2 of t, the term will collapse to just g hat of 0, and so the series grows geometrically with n for fixed values of t. By then carefully isolating the terms of chi-q hat that failed to converge, what we then were as n to a limit, as n approached infinity, we were able to break chi-q n. We were able to write chi-q n hat as chi-q n hat equals stuff depending on n and t, which diverged, plus stuff depending only on t, which did not diverge as n approaches infinity. So as of June 12th, 2024, when I was writing this, and as an update, as of Sunday, July 7th, 2024, when I'm making this presentation, I do not know if the same trick will work for frn hat. I have spent hours and hours doing this, trying to replicate the computation we did for chi-q hat for frn hat. And I have not been able to get the correct answer, and I've in fact done it multiple times. Just as reminder, the idea of the computation is that once we take our closed form expression for chi-q n hat, if we subtract off and pull away all of the terms that diverge with respect to n, what remains should then be the correct formula for the Fourier transform of chi-q. So what the problem here is that when I try and do this for frn hat, when I subtract off the terms that diverge as n goes to infinity, what's left doesn't generate a Fourier series which sums to frn of t. Now what's important about here is that because this computation is so horrific, I genuinely don't know if the reason why my computation method fails here is because either I'm just screwing up somewhere, or if there's something fundamentally different about computing the powers of about computing the Fourier transform of the powers of a quasi-integrable function, as opposed to computing the Fourier transform of the original quasi-integrable function. Just as a quick reminder, back in episode, I think it was episode 7. Back in episode 7, we did this lengthy computation right here, following along the lines of what I did in following along the lines of what I did with a chi-q. We showed that if we define the F series S by this sum, where F is this product, we then found that it had a Fourier transform, and the way we did this is exactly as I described. We computed the nth truncation, took its Fourier transform, extracted the non-divergent terms, and then those magically happened to be the correct formula. However, this appears to break down if we consider, say, S squared or S cubed. And so it would be interesting to see if the breakdown of my method is something that is inevitable, or again, if it's me just making a mistake, or if there are certain cases where the method does not break down. One of the reasons for this, to get a bit ahead, is that if it is true that basically the whole point here is my method for computing chi-q hat seems to detect whether or not I'm working with a quasi-integrable function or the power of a quasi-integrable function. This has an analog in commutative algebra from the notion of the radical of an ideal. For example, both p and p squared, where p are a prime number, belong to the ideal pz of the integers. However, p generates that ideal, while p squared does not, and then the radical of that ideal, of course, is just the ideal generated by p. So in this case, there's a fundamental distinction between p squared and p. We can, in the integers, we can get smaller by going from p squared to p, but we can't continue to go down that road, because then that would take us to the square root of p, which is no longer an integer. What my methods seem to indicate is that when you have a quasi-integrable function, the nth root of the quasi-integrable function is not going to be quasi-integrable, and in order to compute the Fourier transforms of the powers of your quasi-integrable function, you're going to need to do some trickery involving linear algebra, and generators and relations in order to get what you want. And we're going to see that right now. So what we're going to do here is instead create success from failure. So as I said, and in particular, because it's so horrible, we're just going to do, for now, the case where r is equal to 2. So we're going to be computing the Fourier transform of this series squared when p equals 2. For the r greater than or equal to 3 case, I have a also horrible but more practical, slightly more abstract argument that allows us to do it for all the r's with only one horrible computation instead of infinitely many. So in my work, whenever I ran through my episode 4 procedure, I would end up with an expression of the following. Frn hat of t is equal to some linear combination of functions g1 hat through gm hat plus the divergent part. Yeah. I then computed the Fourier series, and so yeah, I then computed the Fourier series from these, and I realized something. If I can even if this formula is not the correct Fourier transform of fr, perhaps we can choose scalars b1 through bm such that we can correct this and yield the correct formula. And so then this, amazingly, it turns out to work. So in other words, by performing this asymptotic analysis, I figure out what the shape of what this sum looks like, which then tells me the functions which I need to consider linear combinations of. Then it's just a lengthy matter of carefully doing the linear algebra to figure out exactly what the correct scalars are. So while this does work and it does yield explicit formula, the problem is that, again, it gets exponentially more complicated as R increases, because we're going to have far more functions to deal with and far more identities, and it gets messy. And this is only for f-series of a two-adic integer variable. When you get into foliated f-series for p-adic integer variables where p is an odd prime, it gets even crazier. So what we're going to do then is we will first, to cover the direct approach, I am just going to show you the functions that I got from this, because, again, the computation would take probably over an hour just to get through the whole thing. And I'm just going to show you that everything manages to work. So we're in here, to make this case more manageable, we are first going to need some notation to simplify it. So to begin with, let's let n be a non-negative integer and let q be any algebraic number. Then I define the functions pi qn hat and pi q hat. These are functions from z2 hat to q bar. They're defined as follows. Pi qn hat of t is 1 if n is 0, and is the product of this guy from n equals 0 to big N minus 1 otherwise. And pi q hat of t, on the other hand, looks like this, and the upper bound is negative v2 of t minus 1. These functions are meant to generalize the aq hat function we worked with for chi q. Indeed, we have that aq hat is equal to pi q hat over 4 to the negative v2. The pi hats play a central role in the analysis of frn hat, by virtue of the untangling property that we saw in AQ hat back in episode 4. Specifically, we have the following relationship. For q algebraic number, a non-negative integer n, and for t in z2 hat, we have that chi q n of t is equal to itself if n is strictly less than or equal to negative v2 of t. And this is trivial, so obviously, but here's the interesting part. If n is greater than or equal to negative v2 of t, and technically I suppose this should be for non-zero t, because if t is 0, this is going to be negative infinity. So if for non-zero t, if n is greater than or equal to negative v2 of t, we can then pull out the geometric factor, and we get that this is, this works here, because I said it, so if t is 0, this is going to be negative infinity, and so then this is going to be infinity, and then the minimum of infinity and 0 is 0, and so yes, it all works. So yeah, this formula holds for everything, and so this allows us to go from the partial product to this product bounded in terms of the two-adic valuation of t. And then it shows the geometric factor we accrue when n gets large. And the proof is just break up the product. So naturally, when introducing a new function out of the blue, it's nice to know where said function came from. And for the pi hats, the answer to that question is the following integral, which will appear when you start churning out the asymptotic analysis for frn hat. In particular, the integral of q to the number of 1s in z mod 2 to the n, it's the Fourier integral of that function, is given by two things. And this works for any algebraic number that's not q, which is non-zero. We get this formula in the case where q is equal to negative 1, and this formula in the case for all other q. And the reason why is we can think of this as this is the particular limiting case where we have when this goes to 0 as q goes to negative 1. And just to note, this works for any algebraic non-zero algebraic number. In fact, it works for any non-zero p-adic algebraic number, because this function here is locally constant. So that's the trick that underlies everything, is what we discussed in episode 4. As long as you're dealing with locally constant functions, integrals are the same thing as finite sums, so you don't need to worry about matters of convergence. It's just linear algebra all the way through. So for this, we simplify the sum, and we simplify the sum of the Fourier series. And we're going to show that this Fourier series, in fact, generates this thing. Starting with this formula, we do our standard trick of summing over the level sets, and then we use our favorite identity for generating functions, which says that this thing is going to be equal to the sum from k equals 0 to 2 to the n minus 1 of q to the number of 1s in k times e to the negative 2 pi I kt, which is here. We then use our Ramanujan sum trick, and as we're familiar, we then use this to express the exponent here in terms of z, and then this reduces to a telescoping series whose sum is this quantity. So we have the following identity for all n. And so if we multiply by q plus 1 over 2, all to the power of 2 to the n, all to the power of n, we then find that this integral is equal to what we want here. And as for the q equals -1 case, it's the q equals -1 case. Here, by definition, because this is a locally constant function, this is what this integral reduces to, which is of course just this by our generating function identity. And then here we then take care of n as n gets large. In particular, if n is greater than or equal to negative v2 of t plus 1, we then have that for n equals negative v2 of t, this is 0. And so when as n gets bigger, for fixed t, the terms of this product go to 0. So in order to avoid this, we need to have n being less than or equal to negative v2 of t. And that requirement then gives us that n 2 to the n, in fact, actually has to be equal to the absolute value of t. So this is going to be, and then the indicator function here can be, this bracket can be written like this, because just look through it and you'll see that it works. And so that clears everything we want. And so again, also this formula here will work if we treat this quantity as taking values in any field, that as long as the field has characteristic not equal to 2. And also the field needs to contain a primitive 2 to the nth root of unity. So then here is what the linear algebra comes from. So when I ran through my computations, I ended up finding that the functions which kept appearing as those g hats were these guys. The Fourier series generated by pi a hat, the Fourier series generated by pi a hat over b to the negative v2, and the Fourier series generated by v2 times pi a hat over b to the negative v2. So in this case, what we really have is we have 3 linearly independent functions. And so we're going to be studying them. And the proof of going through the Fourier series, it's just straightforward. So here we start with, this is just directly the level set sum. And here a and b are non-zero parameters. And little m and big M are non-negative integers, and z is an arbitrary 2-adic integer. So for 1, we just use our standard trick. This is the definition of pi a hat. We then use our generating function identity. We then swap the sums and collect these two terms. We then do the Ramanujan sum trick, and then we re-index the series and write things in terms, write k in terms of z, and we get that, which is nice. As for the sum, well, we've just computed the individual level set, so this whole sum, and remember here t is non-zero, this is just going to be the sum of this quantity from little m equals 1 to little m equals big M. And we do that, we have our telescoping series, and voila. Since pi a hat of 0 is 1, to include the t equals 0 term, we just add 1 to both sides, which gives us this. And of course, that's exactly what we claimed. Here now we're going to be considering this factor right there. And for that, we're going to use our level set sums. Summing over the level sets, here it's n equals 1 to big N, and we pull out the b to the n. We then use our formula for, this is redundant, we then use our formula for this level set sum, and then we pull in the b1 over b to the n. We rearrange things, cancel out the telescoping terms, and we have the following. Finally, for 3, we apply proposition 7 all the way back from episode 1, which told us how to compute the partial sum of the Fourier series generated by v2 of t times mu hat of t, when mu hat of t was already known. And that's just by directly applying that formula, we get this thing. Though, as I said, though we will not go through with the asymptotic analysis here, it's worth mentioning the setup that I used for it. So formally, using the f-series for xq2, the Fourier integral of that is this thing. So we then rewrite this as a product, and then we do the snake oil of exchanging the sums in the integral. So what this then says is that if, at least to make this rigorous, is if we want to make sense of this integral, it seems that we should proceed by investigating this integral. And so by computing a closed form expression for this Fourier integral, we could then attack this sum and try and make sense of this. So untangling this would involve using proposition 127, which is this guy right here, to then untangle things as n goes to infinity. Another method I use, which is along the lines of the recursive argument we gave for chi-q hat in episode 4, the other argument would be to proceed directly with this functional equation and to try and find a closed form for it. To do this, we're going to set r equal 2, and when you do that, you end up with, where is it? Yes, you end up with this thing. So f2n hat of t is equal to this function plus f1n minus 1 hat of 2t plus f2n minus 1 hat of 2t. The trick here is to note that this function is the Fourier transform of the n-1th truncation of xq2. However, we know that by the f-series for chi-q, xq2 is equal to 2 times q minus 1 times chi-q plus 2. And so the n-1th truncation of this thing is the n-1th truncation of that thing. And since we already know a Fourier transform for chi-q hat, we then have that because this is the n-1th truncation of this thing, this should be the Fourier transform. And so we can then plug this in, and that then gives us a recurrence relation between f2n hat of t and f2n minus 1 hat of 2t. And here we would use our formula from episode 4 for the closed form expression for chi-q hat n minus 1 of t. And here we have alpha q of t and beta t. And then we plug things in and we get a recursive formula which we can then attack using our untangling proposition with the pi hats and pull out the divergent terms. So as I've said, it remains to be seen whether or not either of these approaches that I've just described actually give the correct answer. Nevertheless, as I said, even if their answers aren't quite right, we can use the general shape of their non-divergent terms to then find a closed form expression for f2 hat using linear algebra. So, and as for the integral of xq2 squared, it's worth noting the following computation, which is that the integral of q1, number of ones in z mod 2 to the n1, times q2, number of ones in z mod 2 to the n2, the Fourier integral of that is this. And so here we're going to assume that n2 is greater than or equal to n1. So what ends up happening is that you have these products that start interacting with quotients, and in particular we have the following special case. In case both n2 and n1 are bigger than the negative 2 Adic valuation of t. So what this is then saying is that this Fourier integral, obviously, it's going to depend on the relationship between the 2 Adic valuation of t and n1 and n2. So understandably, if we added q3 and to the number of 1s in z of 2 to the n3, we'd then have to take into account all the different possible ways that n1, n2, and n3 can be ordered in terms of increasing size. And the proof, it's just index, it's bookkeeping. So since this function's n2 is bigger than or equal to n1, this integrand here is locally constant modulo 2 to the n2. So this reduces to this sum. Then what we do here is we simplify things by breaking it up mod 2 to the n1, so that both of these reduce to sums. We then use the properties of the number of 1's function to break this up into a product, and then we use our generating function identity, and then the rest is about playing around with indices. And when n1 is n2 is strictly greater than or equal to n1, which is greater than or equal to negative v2 of t, we can then use the untangling proposition. And note, this is the interesting part, is that once t, what this is saying is that if t is closer to 0, if v2 of t, negative v2 of t is closer to 0 than the n's are, then this function behaves as if it's just the product of q1 times q2 to the number of 1's in z mod 2 to the n. So later on I will give a version of this formula for the kth power of xq2. So, but anyhow, regardless of which method we'll use for our asymptotic analysis, as I said, as a q varied, we end up with the following non-divergent terms. They look like this. So we had pi a hat over b to the negative v2, v2 pi a hat over b to the negative v2, pi a hat over b to the negative v2 times this sum, 1 over d to the n, a squared a, and this sum here where we multiply it by v2 of t. So 4 terms. Here a, b, and d are just parameters, and all of these are defined for non-zero t, but they can be made to make sense at t equals 0 in a very natural way by replacing every instance of negative v2t with the maximum of negative v2t and 0. When t is 0, this will be the maximum of negative infinity and 0, which is obviously 0. Of these, most important is the third, which very much resembles the integral we had for xq2 squared, and in particular, if we set q1 equals q2 equals a, we saw that this integral, this is what we get when n2 is greater than or equal to n1. So now finally, to deal with this guy though, we're going to need to introduce yet more notation. And this is just to make things simple. So for any integer n and parameters a, b, here we can just treat a and b as formal indeterminates. We define Sn of AB is going to be this nth partial sum of this F series if n is greater than or equal to 1, and it'll be 0 if n is less than or equal to 0. Taking away the n then is the same thing as letting n go to infinity. And again, we're treating this just as a formal expression. And from here on out, everything is a matter of algebra. No analysis. Well, there's a tiny bit of analysis involved, but it's almost negligible. So the first identity, let a, b, c, d be parameters, and just assume for safety that none of them are 0, and let m be a non-negative integer. Then Sm of ab times Sm of cd is Sm of acbd plus 2 times this sum here. As usual, we will define the sum on the far right to be 0 whenever m is less than 1. Proof, just basic grade school algebra. So here's the product of SAMB and SAB and SCD. We then have this here, and then we use just the standard symmetrizing that the middle terms, it's equal to twice the sum from m equals 1 to m minus 1 times the sum from n equals 0 to m minus 1 of their product. These, of course, combine, and voila. So next, we tackle the partial sums of the Fourier series generated by this guy. Yes. Now, I just actually had to spend like maybe an hour and a half retooling the document because I'd made a minor error and a major error. The minor error is both minor but important. Originally I omitted this denominator factor of 2 to the n over 2 to the n to n2, which is very important. The other thing is that there was a computation that I've been so involved with when I was doing it that when I was doing it in a separate document, and when I finally got it to work, I forgot to paste in the details, so I had to reconstruct them, and now that's taken care of. So we're going to be using this formula and we're going to into the case specifically where Q1 and Q2 are going to be equal to our parameter A. So in order to tackle the Fourier transform, or sorry, the Fourier series of this guy right here, we're going to break the problem up into several steps. So the first step is this Fourier identity. So using our integral proposition with Q1 equals Q2 equals A, we have this, where here n2 is greater than or equal to n1. In this particular sum, m is strictly greater than n, so here we'll set n2 to be m, and set n1 to be n, and then we get the following. Now, this function right here, since m is greater than n, this is locally constant modulo 2 to the m. As such, it's by Fourier inversion, we need to multiply this by e to the 2 pi I tz, then we sum from over all t with a 2 Adic absolute value less than or equal to 2 to the m, and the result will necessarily be equal to this product. So the Fourier inversion tells us this thing. Now we note a trick. Here, m is greater than or equal to negative v2 of t, and so by our untangling proposition, pi am hat of t is actually 1 plus a to the m plus the minimum times pi a hat of t. So we pull out the powers of m, and we get this. So far, this holds when n is less than m. Since since n is less than m, we also have that n is going to be less than or equal to m minus 1. So this formula holds when we replace m with m minus 1. Because, again, n is still less than or equal to, is then still strictly less than or equal to this thing. So now we're going to divide this equation by 1 plus a over 2 to the m, and we divide this equation by 1 plus a over 2 to the m minus 1. Then, because note that these have the same Fourier series, so when we subtract them, what we're going to get is this thing, but take away every term less, so all that remains is the level set sum when t2 equals 2 to the m. Since t2 equals 2 to the m, the minimum of v2 of t and 0 evaluates to negative to an m, because v2 of t in this case is negative m, because we're doing a level set sum. And so now all we do is just multiply by 1 plus a to the m on both sides and simplify. And then we can pull out this common factor of a to the number of 1s in z mod 2 to the n, and that gives us our identity. Now here's where the nonsense gets started. And I know that the nonsense has begun because I've started labeling things. In my computations, I'll have like a full 3 or 4 line thing, and I'll say with brackets, let this part be A or 1, or this part is B or 2, and then I just do things. This shouldn't be italicized for whatever reason it is. So here, let's let 2m of ABD be given by this Fourier series. Then 2m of ABD is equal to this messy expression. And the proof is that we're going to begin by attacking the level set sum. So here we can use our identity that we just proved. So here we just swap the t sum and the n sum. By the identity we just proved, that is equal to this. Here we can distribute the b to the m, and here we're only going to give b to the m minus 1, so that spare value of b goes over there. This is dependent on n, this is independent of n, and so this here is Sm of AD, and that's the difference. So if we now sum this, or from m equals 1 to big M, we get the full Fourier series. So this is equal to that, where we've used the level set sums, and we've swapped the n sum and the t sum. This, as we just saw, is equal to all of this thing. This right here is that. And so now we just have this, but we're summing from little m equals 1 to big M. We split this up, and now note that S sub m plus 1 is going to be equal to, because Sm is the sum of the a to the number of 1s over d to the n for n equals 0 up to n minus 1. So Sm plus 1 is just this. And so using that in here, note that so when we distribute this term, we're going to get a squared over bd over 2 to the m plus that term times that term. So this, of course, is S big M of a squared of bd over 2. Here we can combine these two by just re-indexing. Note that when we pull out the m equals 0 term, S0 of AD is going to be 0 by definition. And so we end up with this thing. Now what's left? Well, I want to get rid of this guy, and which we can do by using our multiplication identity. In particular, when we replace b with b over 2 and set c equal to a, our proposition 131 identity is this. So now just subtract this term and then divide by 2, and we have that this term is this thing, which we then plug in. Finally, we just collect terms, and in particular, this term is going to combine with that term, and that's the double negative. The negative here and here will then turn it into a plus, and so that's our desired result. So, importantly, note that through all of this computation, with the lone exception of the occurrence of z right here, we really didn't care about z at all. Indeed, what mattered far more than z were the parameters a, b, and d. This then leads to what I think is the most exciting step of the whole computation. We are going to need to introduce derivatives of formal power series, and more generally, derivatives of formal rational functions, and more generally, derivatives of formal power series. So Sm of AB, just go back to the definition, Sm of AB, we recall, is this guy. For Sn here, this, ignoring the value of z, this is a rational function of a and b. So therefore, it's an element of the ring of such rational functions, and one of the things you do when you have a rational function is you can consider its derivatives with respect to its parameters. And in particular, we have that I'm going to write Sm prime of AB to denote the formal derivative of a, this should be a big M right here. This should be S big M prime is the formal derivative with respect to B of S big M, which then, of course, here, this is B to the M, same thing as B to the negative M, so we're going to multiply by, that's going to become negative M times B to the negative M minus 1, and so we have that this is equal to that. Before we proceed, it's worth noticing that we've already actually used these kinds of formal derivatives. In fact, we've been using them since episode 1. If we look at this formula, and again, we just ignore t and view this as a rational function of a and b, here, if we set a and b equals 3, we would get this. And the thing is, if we get rid of this v2 of t, we can obtain it formally by treating this rational function of a and b, and we just differentiate with respect to b. In particular, the partial derivative of this with respect to b is the same thing as that. We then get v2 of t, b v2 of t minus 1, and so the partial derivative of this with respect to b is all of this. So in other words, if we multiply through by b, to go from this guy to this guy, all we need to do is differentiate and multiply by b. This operator here is very well known. It's known as the homogeneity operator because its eigenfunctions are the functions of b to the n. The homogeneity operator sends b to the n to n times b to the n. And this is a fundamental class of differential operator. And because and the fun thing is, because we are dealing with F-series and their Fourier transforms, observe that these formal derivatives can then be applied to both the F-series and their Fourier transforms. And this is going to be very important because by combining the linear algebra we've done here with the formal derivatives, we'll be able to take care of all the possible cases. We won't need the formal derivatives for the q greater than or equal to 5 case, but we will need them for the q equals 3 case. So in particular, we have the following relationship between our sums and formal derivatives. This relationship is actually the proposition, actually I'll get into this in a moment, it's the proposition we saw with v2 of t in disguise. And what it says is that if we sum Sm from m equals 0 to big M minus 1, this is by summation by parts, this is the same thing as big M minus 1 times Sm big M minus 1 of AB minus B times S prime of M minus AB. Here we just write out the sum. Note that this is by our convention is 0 if M equals 0. Now we're going to swap the m and n. Here n takes values less than or equal to m minus 1, which means that if we swap the order, m must take values greater than or equal to n plus 1. This is independent of m, so we just get the m minus n minus 1 term. And here, this n goes there. And this, of course, is precisely b times s prime of m minus 1 of ab. In other words, and also b times the derivative, that's just the application of the homogeneity operator. So what we're saying is that summing this term, the series is the same thing as m minus an application of the m times the thing minus an application of the homogeneity operator. And using formal derivatives, we can then rewrite these two sums that we computed earlier. We can rewrite these as this and this, because again, if we view this, both sides are rational functions in B, we just formally differentiate them with respect to B, and we get what we want. Please tell me that I did that properly. There might be a negative sign off. It does not affect the answer, but this is the kind of this is the kind of bullshit I've been dealing with. Let's see. Does the negative sign actually impact the answer? It's b to the v2 of t, v2 of t, and then actually no. It's there. It's fine. It's supposed to be there. Here, the exponent, it's going to be negative, but here, note, it's b to the m, so when we put that up top, it's b to the negative m. Yes, I'm not crazy. It's just... Help me. Wait, did I forget a multiplicative factor? No, I did not. Because we have the derivative by the chain rule, and bm should be an m minus 1. And yes, and then we multiply through by b on both sides. Yes, so, yes, this is correct. This is completely correct. As I was saying, this identity, the presence of this link between this summations and formal differentiation has actually been present since episode 1. There we proved the proposition that if we had a function mu hat of t, and we knew what its nth Fourier series mu n was, then the Fourier series generated by v2 of t times mu hat of t was given by this thing. So what this is then saying is that when we view things in terms of formal polynomials, the formal differentiation in F-series space is the same thing as multiplying by v2 of t. Well, I should say the homogeneity operator in F-series space is the same thing as multiplying by v2 of t in Fourier transform space. I feel, and I'm going to get into more of this into just a bit, but I feel this is really exciting because it means that we can now bring in the tools of commutative algebra. Actually, I should say it's non-commutative algebra, because we'll be considering algebras of formal differentiation operators. And in fact, there's significantly up. There's more detail we can get into this, but I'll save that for later. So now, because this is my computation, this is what we're going to need for the specific case where q is equal to 3. We're going to define pi 2 prime of m of a, b, d. Why? It's just going to be the homogeneity operator times what we had. And then, in particular, I'm going to be dealing just with the case when a plus 1 is equal to b. Then we have 2m prime is equal to this guy. And so the proof is we're going to be using our proposition 7, which is this guy. We're going to be using that on proposition 129, which was our computation for 2, since the 2m prime has a Fourier series which is obtained by multiplying 2m's Fourier series by v2, we know that the Fourier series of this guy is going to be, the sum is going to be negative m times 2m plus this particular sum. So we then apply this to our formula for 2 of m, and we get this nightmarish thing. And now we get cancellation. So we're going to set a, to make this simple, set a plus 1 equal to b. So that means this dies, and this then is going to be equal to 1. So this becomes 1, and that becomes 1. And we're left with this. Now, once again, we're going to use our product identity to transform these sums into products. And in particular, we apply this for down there, and we have 2 prime is equal to all of this. Finally, so we're going to use our formal differentiation to write this in terms of the formal derivatives. And in this case, again, we're using the chain rule, so instead of b, it's bd over 2. And so with that plugged in, we then get this and simplify. But in other words, the whole point of all of this is that we're using linear algebra to reduce everything to sums of products of SMs and their formal derivatives. And those are the relations that we're using in order to get what we need. So, yeah, as you may have already noticed from the a plus 1 equals b constraint, so this here we're going to be setting b equals 4 and a equals 3. For all the others, we won't need it. So now let's just proceed. We're going to set a equals 3, b equals 4, and d equals 2. Then, the series of x 3, 2, which is 3 to the number of z, 1s and z mod 2 to the n over 2 to the n, that's going to be manifested as s of 3, 2. So by setting a equals 3, b equals 4, d equals 2, our above propositions tell us that 2m is equal to this thing, and 2m prime is equal to this thing. So Sm of 3, 2, as m goes to infinity, this thing is, ignoring this term, this thing is going to converge to x 3, 2. So what we're looking for then is this term right here. As m goes to infinity, this is going to converge frame-wise to x 3, 2 squared. So all we need to do is use linear algebra to find the appropriate relations to this. And so here, we're going to do this is the little bit of analysis that I mentioned. We're going to just do things with respect to the simple 2-3 Adic frame. Here, as m goes, since this series and this series both converge with respect to f2-3, and this thing converges to 0 with respect to f2-3, we then see that 2m, as n goes to infinity, is going to converge to negative s of 9, 4, while 2 prime at infinity, this is going to die here in the 2-3 Adic frame. Infinity prime, this is going to be 1/2 s of 9, 4 plus 1/2 of s squared of s of 3, 2 squared plus 4 s prime of 3, 4. Consequently, 2 times 2 prime infinity plus 2 infinity is equal to s of 3, 2 squared plus 8 s prime of 3, 4. And so just the proof is just by direct observation, and then just here we just then now to use linear algebra, we're going to add one of this equation to two of this equation in order to cancel out the 9 4s, and we have this. So what this says is that in order to find a Fourier transform for s of 3 2 squared, we just need to find a Fourier transform for s prime of 3 4, and then subtract 8 of it from this. And for this, we're going to use our previous proposition by way of our remark, which said that so in this case, I'm going to take b and replace it with 2b. We then have these two formula. So set a equals 3 and b equals 4. We then get this identity and this identity. Taking the limit as m goes to infinity, we then have the simple f(2,3) convergence. This is going to be -1 plus 1/2 s of 3 4, and this is going to be 1/2 s of 3 4 minus 1/2 s of 3 4 prime. Also, note that we shall not need it here. Note that this convergence on both of these lines doesn't just occur three-adically. Actually, both of these series converge uniformly in the topology of the complex numbers with respect to z, because S34, that F series is by the M test. It's uniformly bounded by the sum n equals 0 to infinity of 3/4 to the n, which is, of course, just equal to 4. So what we then have is just, let's do the linear combinations. Let's call, here I'll just modify the formula here to add in a 1, and let's call this 1 infinity, and call this 1 infinity prime. We then have that 2 times 1 infinity minus 1 infinity prime. So 1 infinity minus 1 infinity prime is 1/2 s prime of 3 4. So that then tells us that this is equal to s prime of 3 4. And again, because this is frame theoretic, we found our Fourier transform for s prime of 3 4. So we have 2 prime infinity plus 2 infinity f(2,3) is equal to s squared of 3 2 plus 8 s prime 3 comma 4. So now we're just going to subtract 8 of this guy, and then we have that the 2 prime infinity plus 2 infinity minus 16 times 1 infinity minus 1 prime infinity is f(2,3) convergent to s squared of 3 2. And so this the left hand side of this formula is a Fourier series, and so we just read off its Fourier coefficients, and that will then give us our Fourier transform of s2 of 3 2 squared, s3 2 squared, which is of course just x 3 2 squared, aka f2. So for non-zero t, the Fourier coefficients here are as follows, and when t equals 0, the Fourier coefficients are that. And so adding everything together, voila, there is our formula for s of 3 2. So this is, and in particular for s of 3 2's Fourier transform, so that's f2 hat. Now we're going to use this to recover a Fourier transform for chi3 squared. We use the fact, this is again, it's the F series that we gave at the very beginning of episode 1. S of 3 2 is equal to 4 chi3 plus 2, so we square both sides. And so identifying the Fourier transform of chi3 2 with a chi3 hat convolved with itself, the Fourier transform of this guy, on the left-hand side, this is going to be 16 chi3 hat convolved with itself plus 16 chi3 hat plus 4 times the integrator function of 0, which then is going to be equal to the Fourier transform of s3 2 squared. And so because of this, since we already know a formula for chi3 hat of t, we then just do our little algebra, and we end up with blah, 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 and we then have, at the end of our result, we have this particular formula. And with this, we have finally proven chi3 squared is quasi-integrable with respect to the simple 2-3 Adic frame. The formula blah is then a Fourier transform of chi3 squared, and the Fourier series converge. So part of me worries that I screwed up somewhere, and as such, this might not be the right formula. Even if that is the case, however, the structure of the argument remains valid. We just take linear combinations of certain Fourier series and then use the known formula for chi3 hat to produce a formula for chi3 hat star 2 star. And in particular, what this then shows is that, because remember, for a quasi-integrable function, the Fourier transform isn't unique. It's only defined up to the Fourier transform of a degenerate measure. So what this then says is the Fourier transforms of chi3's powers will then inherit that same dependence, although instead of being a linear dependence, it'll be nonlinear, because we'll have to deal with that. But actually, no, it will be linear, because we then add or subtract the 16 from that, and we get what we need. Yeah. So next we tackle the q greater than or equal to 5 case. Unfortunately, this one is significantly less horrible. So using proposition 133 with a equals q, b equals 4, and d equals 2, where q is bigger than or equal to 5, we get this. And so taking the limit as m tends to infinity, we get convergence with respect to the simple 2q Adic frame. 2 infinity of q42 is equal to this minus this. So all we need to do is find a Fourier transform for s of q squared 4, and we can do this using a equals q squared and b equals 8, blah. And so then let's call this im of q squared of 8, and then let's limit I infinity of q squared 8, that's equal to that guy. So then doing our linear algebra, we then end up with s of q2 squared is f2q convergent, as this is its Fourier series representation. And so reading off the Fourier coefficients, we get this. Like with chi3, we then use this relation and go through the algebra, and we get all of this stuff and these fascinating polynomials that appear. And so here I just use Wolfram alpha to get the thing. And so there's the formula for chi q hat the star 2. And so this then proves quasi-integrability for that guy. So by a minor miracle, the t equals 0 term of this thing actually agrees with one of the few cases of the asymptotic analysis in the style of episode 4 that I've managed to do by hand without incurring too much self-doubt on my part. So we start with the identity here, which is our product identity when q1 equals q2, and here it's both. No, here, this we don't need to worry because t is 0. So this is holds for all m and n. So with this identity, we then get that it was just by summing. So the integral of the square, since we're summing only a finite sum, everything works here. So we then break up our summand in the notes that since this summand is a symmetric function of m and n, we get that this double sum is equal to that plus that. And so we get this. So for me, imagine doing all of this, but it's not just the integral, it's the Fourier integral. And so you have to deal with all the difficulties. So here I just gave up. Let's let Wolfram alpha do this for me, which we get this. Now, as we did in episode 4 and episode 7, just discard all the divergent terms. So you go away, you go away, you go away, and you go away. And so this then leaves us with -1 over that, plus this whole thing goes away. And then we left with a negative that times -1, and this simplifies that. And look what we got. This is less pretty. Yes, this is. These two end up being the same because you have to multiply out the full thing. Here we go. There's the term. Yes, here. Sorry, no, there it is. It's right there. 8 times q plus 5 over q minus 3 times q squared minus 7. And likewise, when the integral, we get the same quantity. So, which is precisely the 0th Fourier coefficient of S2Q2. So this general pattern actually held true even back in the r equals 1 case. There we saw that the nth Riemann sum of chi q, which is the same thing as the integral of this locally constant function, is equal to this. If we drop the divergent terms, we get 0 and negative 1 over q minus 3, which are precisely the values we computed for chi q hat of 0 in episode 1. This would suggest that perhaps the reason the direct analysis has failed might have been due to an error on my part. Well, we can even check the q equals 3 case, and here this is actually computable in closed form. So we have this, setting q equals 3, we get this, blah, 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 we get all of this. So this is where something interesting happens. Note that in the q greater than or equals to 3 case, we had these terms, we had this series where there are divergent terms which are all geometric form. However, here, we have this non-divergent term negative 36, which disagrees with the formula answer that we got, which was, just to go back, for S2, the Fourier transform of S32 squared, it was negative 16 at t equals 0, which disagrees with this formula. That being said, note that the n here creates an ambiguity. When the q wasn't equal to 3, we got this, and here, changing the value of n did not alter the non-divergent terms, because what changing the value n does simply multiplies the divergent terms by a factor. However, here, because this is not geometric but linear, if we shift n, like say by n to replace it with n plus k, we end up getting this, and so that's a completely different non-divergent term. Thus, the drop divergent terms approach is ill-defined for q equals 3. In fact, this is also true for the r equals 1 case. However, there, dropping the divergent term to get 0 produced the correct answer. In light of this, perhaps I did actually make a mistake in the computation of this Fourier transform, or perhaps there's something deeper going on. Again, whether or not these errors exist has no bearing on the correctness of the idea overall, and as the next section will show. In order to keep this from being like a 4-hour-long episode, I'm going to split it up into several parts, so the next part will be dealing with the general case. And that's it for now. See you in the next video.